All right, so I think this is recording. Let's take a look at these problems. Most of these are just calculator exercises. So let's take a look at this number one. I'm going to set the calculator to radians. Yeah, it's in radians. 4 decimals is fine. So my answer for number one, take the inverse sine of 2/5. And there's my angle measure in radians for number one. All right, let's go on to number two. Let's take the inverse cosine of -3/4. And here's the angle measure in radians of 2.4189. You can check it by taking the cosine of 2.4189 and getting -3/4 as a decimal there. All right. And see, these are all functions. Every input has exactly one output because of the capital letters, because of the notation. All right, so for number three, I get an angle measure in radians of 1.4056. For number four, take the inverse cosine of 7/8. You know, just make sure that you understand whether you're in degrees or radians. Really, we could be in degrees because the problem really didn't say. I'll try to be more specific. I will be more specific on the test. Arc cosine is just a different notation for an inverse cosine. Don't let the different notation bother you. There's our answer for number five. Arc tangent, the same. It's the same as inverse tangent. When I say the same, I mean the same comments. So here's the angle measure in radians. And again, you know, if you want to check tangent of 0.5191 is going to be approximately what 4/7 is. So you can see at least 4 decimals that it's the same. Sometimes you may have slight round off error, depending upon how many decimals you carry it out to. Just the problem. So here's our answer for number seven. Inverse cosine 0.991. There's our, and remember, you know, it's the input into an inverse trig function is a ratio, and the output is an angle measure. So do try to keep that in mind. Alright, so now the directions change, and now I don't have a capital letter. I'm going to have more than one answer on these. So let's take a closer look at this then. If I look at my unit circle for just a moment, I don't have a y value on here anywhere of 2/5. Now, because our unit circle is a nice tool, but once you begin to think a little bit more about it, it's kind of limited to just two triangles, a 30, 60, 90 degree triangle and a 45, 45, 90 degree triangle. And of course, our knowledge is on if you're on an axis. So there's infinitely many points on this circle, and we're only focusing our attention on just a few, you know, just a small few when we're working with this unit circle. I know that somewhere on this unit circle that there is an x-coordinate of 2/5, that there is an x-coordinate, because I know that the domain for this function is from -1 to +1, and 2/5 is between -1 and +1. In fact, there's going to be, remember that the sine is the y coordinate. So there's going to be a y coordinate of 2/5 here in quadrant 1, and then over here in quadrant 2, because the y tells you your height above the x-axis. So there's 2 points on this circle that are going to have a y coordinate of 2/5. They obviously don't have the same x coordinate. They're the same in magnitude. One is positive and one is negative because of the symmetry of the problem. Since I don't have the information on my unit circle, I'm going to have to go to my calculator. Now remember, we just got done doing it. The calculator is going to treat this as a function, and it's going to return one value. And see, on 0 to 2 pi, I need two values. So if I say that x is a solution to this equation, the calculator is going to look for a value that's between -pi/2 and +pi/2. So double check that we're in radians, and if I go inverse sine of 2/5, the calculator is going to return a value of 0.4115. And just to distinguish my different solutions, I just arbitrarily call it x1. All right, and that's in reference to this point. Well, I know this angle is in quadrant 1, so it's its own reference angle, and it's this angle right here, which I know is the same in magnitude of this angle over here. So if I'm trying to find this angle that's in quadrant 2, I can use this because this is its own reference angle. If I call it theta reference, that when I come in to find the solution associated with this point, all I have to do is take pi minus, this 0.415. So here, let's do that. Let's just do it on the calculator. Second pi minus my previous answer and 2.7301. So 2 pi is 6.128. 6.28. And I can see that both of these values are positive. They're both greater than 0, and both of these values are less than 6.28. If I take either one of them, and if I add 2 pi, I'm going to be bigger than that because, oops, I don't know what I just hit there. So see, I'm bigger, and obviously if I add 2 pi, I'll be at 6.6, I'll be bigger. So if I want to check these answers, I can take the sine of either one of these, and I should get something that's approximately 0.4, because 2/5 is a decimal, is 0.4. So if I check this other one, so both of those are the solutions to this problem. Alright, so let's move on. Again, we're going to look at solutions between 0 and 2 pi. So with cosine, let's go into a little bit more detail. Here cosine is negative. That's going to happen in quadrants 2 and 3 because you're left of the y-axis. So on this unit circle, since this input is between -1 and +1, I know that on this unit circle there's 2 points that have an x coordinate that, excuse me, I had to sneeze real quick. Alright, so I've got 2 points that's a -3/4. The calculator is going to treat this as a capital C and just a function. this inverse relation as a function, it's only going to look in the upper half of this unit circle between 0 and pi. So when I take the inverse cosine of -3/4, this value that it's returning is in reference to this point that I've highlighted here. Now, right here is its reference angle. So if I take pi minus this answer, I have a reference angle, and I can use this reference angle to get this other angle that I want to get to this other point. So I'm just going to take this reference angle and add pi to it. And there's my second solution. There's two solutions on this, on a single revolution, 0 to 2 pi. See, there's infinitely many x's that satisfy this equation, but only two of them are between 0 and 2 pi. Alright, so tangent. Tangent's is similar. It uses the right half of the unit circle, with the exception that pi over 2, 90 degrees is undefined, so it doesn't use the inputs. But it's going to look here. Now, remember with tangent, we're not looking specifically at an x coordinate or a y coordinate. We're looking at a ratio. Tangent is sine over cosine, or on the unit circle, the y coordinate divided by the x coordinate. And tangent has a negative ratio if x and y are opposite in sign. So I've got a point here in quadrant 2 and a point here in quadrant 4 that's on the unit circle. There's going to be two solutions, two values. There's infinitely many solutions that satisfy this equation, but only two of them are going to be between 0 and 2 pi. And the calculator is going to return angle measures that are between -pi/2 and +pi/2. So when I come in and use this for the first time here, this inverse tangent of -3, this -0.2490 is an angle measure, and it's in reference to this point, and it's going clockwise because it's negative. So I get a solution x that is -1.249. But I have a problem. Yes, that satisfies this equation, that if I take the tangent of -1.249, I'm going to get -3, or something close to -3. It's smaller than 0. So I have the right point there, but I'm going to have to add 2 pi to that to find the angle that I want, which is this angle right here. So if I've got the inverse tangent of -3 that comes back negative, if I add 2 pi, I'm finding a coterminal angle. And my first solution is this 5.0341. Now, I'm interested now in jumping over to this other point. Well, I went past that point as I rotated there. So if I just subtract pi, then I'm at this angle right here. So that's my second solution. And so if we take the tangent of this, we can check our answer. We know that it's going to be approximately -3. Now, because of round off, it may not be exactly -3. So you see it's a little bit big. Before it was a little bit less than, this is a little bit bigger. But those are our two solutions on on that revolution from 0 to 2 pi. We had to be aware that when we used the calculator for the first time, yes, it provided us the solution to the equation, but no, it was not in the interval that they wanted between 0 and 2 pi. All right, so here when we do this, it's going to return a negative value. I know that sine is negative where y is negative. There's 2 points here and here. It's going to return this angle, but that's going to be a negative angle. It's going to be less than 0. And I don't want that as my first solution. Yes, it's a solution to this equation, but no, it's not in this interval that I'm looking for. So second sine -0.718. That gives me an angle in radians. And if I add 2 pi to that, it'll be coterminal, and it'll be bigger than 0. Oops, let's get my 2 in there. So I claim that 5.4823 is one solution. Now let's come back to this angle right here was a negative angle measure, but if I put that point up here, you can see that if I make it a positive angle measure, if I make it a positive angle measure, that they're opposite in sign but equal in magnitude, that this is going to be the reference angle. So I know my reference angle is positive 0.8009, and I know that that's this angle right here as well. So to get to this point, I'm going to take pi plus that reference angle, right? Pi plus this reference angle. So if I get that reference angle and add pi to it, then I have my second solution. Because I was expecting 2 solutions from 0 to 2 pi, the 2 points that I used, that I pointed out here on the circle. And you can check each one of these by taking the sine. And here we get at exactly those 4 decimals. Like I say, sometimes you may have some slight round off error. So here's our 2 solutions. Once again, the first solution the calculator gave back was the solution to the equation, but it wasn't between 0 and 2 pi. So our cosine is going to return a value in the upper half. X is positive in quadrants 1 and 4. So my solutions, my first solution, 0.718 is here. This is one solution. And now if I take 2 pi minus that, it's my other solution. So here's the 2 angle measures in radians that satisfy this equation that are between 0 and 2 pi. For tangent, for the inverse tangent, the calculator is going to look in this right half of the unit circle. Since this is positive, I know tangent is positive in quadrants 1 and 3. So when it returns this first value, that is an angle in radians. It's between 0 and 2 pi. So there's my first solution. See, I'm expecting 2 on 0 to 2 pi. My other solution here, all I have to do is add pi to get there. So my other solution is here. So these are the two values that are answers for 15 that are between 0 and 2 pi. For inverse cosine, it's going to use the upper half of the unit circle. And cosine is positive in quadrants 1 and 4. So I'm using these 2 points. Now this time the directions have changed and I'm going 0 to 6 pi. So I know that on 0 to 2 pi there's 2 solutions. On 0 to 4 pi, 2 more solutions. And on 0 to 6 pi, there's going to be 6 solutions. Okay, but it's going to be very easy using the calculator to get these 6 solutions. This point right here on the first revolution is going to provide 1, on the second revolution a second solution, and on the third revolution a third. Then I can jump down to this point and do the same thing. So let's find the 3 solutions that are associated with this point. The first one being just what the calculator gives me. And now I'm just going to add 2 pi to get the second solution that point gives me. And see, I'm still between 0 and 6 pi. Now I'm going to add 2 pi again. So here's 3 of the 6 solutions that they want. Now let's go back to our original solution, the 3 divided by 8. Now that's in the first quadrant. And when you're in the first quadrant, you're your own reference angle. So this is the reference angle. And so to get to this other point, all I have to do is take 2 pi minus that reference angle. 2 pi minus my reference angle. And so here's my fourth solution. And now I just add 2 pi to it. There's my fifth solution, and add 2 pi to it, and there's my sixth solution. So we found 6 solutions, and you can take any one of those solutions and check it by taking the cosine, and we should get something that's approximately 3/8, and that is 3/8 if you check that, or like I say, there could be slight round off there. So on this tangent, again, we're expecting 6 solutions on 0 to 6 pi because on each revolution, each single revolution, we find 2 solutions. Let's point those out. Tangent is positive in quadrants 1 and 3. So there's a point here in quadrant 1 that if you take y divided by x, you'll get 2. And there's a point here in quadrant 3 that if you take y divided by x, you'll get 2. See, x and y here are both positive values, x and y here are both negative, but when you take that ratio, both of those ratios are positive values. The calculator, when we first go to it, to find the first solution of these 6 solutions, is going to return a value between negative pi over 2 and positive pi over 2. Since this point's in the first quadrant, it's going to return a positive angle measure, so we won't have to do anything with it. Now with tangent, having a period of pi and not 2 pi, it makes these 6 solutions really easy because right now I'm at this point there, and that's a solution to this equation. And now if I just add pi, then I'll be at the next solution, and then if I add pi again, I'm back to that point. So all I have to do is continue to add pi to get these next 5 answers. So there's the second solution, there's the third solution, there's the fourth solution, the fifth solution, and the sixth solution. And I know that this 16.8151 is less than 6 pi. And if I would go one more pi, I'd be going beyond the 6 pi. So those were the 6 answers that were displayed on the calculator. You can pause the video or rewind it and go back and look at those. Here there's going to be 6 solutions again, and sine agrees with the y-coordinate. There's going to be a point in quadrant 1 and in quadrant 2 that has a y-coordinate of 0.655 because that input is in the domain. It's between -1 and +1. The calculator, when we first use it to get our first of these 6 solutions, is going to return a value between -pi/2 and +pi/2. It's going to be a decimal number, but it's an angle measure that's in radians, and it's going to return this value right here. So then, like I say, we're expecting 6 solutions, 3 of them originating from this point and 3 of them originating from that point. So all I have to do once I find that angle is then find 2 more coterminal angles that are between 0 and 6 pi. Let's do that. We've got inverse sine of 0.655. So there's a solution to the equation. If we add 2 pi, there's a second solution. If we add 2 pi, there's a third solution. Okay, those are all coming from that point. Now, to get to this point here, the calculator doesn't tell me this angle right here. I can figure out that angle by using this as a reference angle. So when you're in quadrant 1, you're your own reference angle. So when we took this inverse of 0.655, not only was that a solution to the equation, but it also is the reference angle that's going to help us get other solutions. So if I take pi minus that, see, here's the reference angle right here in quadrant 2. So if I take pi minus this reference angle, then I'm going to get my first of the 3 answers that this point provides, because now I can just find coterminal angles by adding 2 pi. I'm going all the way around and I'm ending up back at that same point. And then I'm adding 2 pi and going all the way around the circle, but I'm stopping at the correct point that has that y-coordinate that's 0.655. So there's my other 3 solutions for this problem. Now, when it's negative, see here, when they're wanting us, now also I just noticed that they've changed to degrees. So let's come in and change from radians to degrees, and I'm gonna, I don't know, round it just to 2 decimals if I'm in degrees. That's pretty common. All right, so the inverse sine, there's 2 points on this circle that have a y-coordinate that's negative, that's below the x-axis. One here, and then come over here and there's that symmetrical point that's the same distance below the axis. Their x's are equal and opposite, but the y values of those 2 points are the same. So the angle that I want associated with this is the angle all the way around here in quadrant 4. But the calculator is not going to give me that angle. The calculator is going to return a value that's between -pi/2, or excuse me, -90 degrees and +90 degrees. And negative, it's going to come back and give me a negative angle measure, which that's going to be smaller than 0. So to then get this with this point, I'll have to find a coterminal angle. I'll just add 2 pi, and then I'll have my first solution. So the calculator returns a value that is a solution to this equation, but not in the interval that we want. So this 0.778, remember, that's from your SOHCAHTOA. That's from a right triangle, the length of the opposite leg divided by the length of the hypotenuse This is just that decimal value of that ratio. When we take this inverse, it's now going to give me an angle measure, and this is now in degrees. But like I say, this is not going to be a solution to this because it's smaller than 0. If I add not 2 pi, but if I add a complete revolution, if I add 360, then there's my first solution. Now on 0 to 720, that's just 2 revolutions. 360 plus 360 is 720. So I'm expecting 4 solutions. Here's one of the 4 solutions. If I add another 360, that's coterminal, I'm still below 720. Both of those are solutions to this equation. If you take the sine of this 668.92, I claim we're going to get something approximately equal to this negative 0.778. And well, I'm fixed to 2 decimals, so yeah, it checks. So now to get to this point, let's come back and use our reference angle. If I take the inverse sine of positive 0.778, then that's this reference angle, and if I add, that's this angle right here. If I add 180 to that, then I get the first of the solutions that this point provides. So if I add 180 to that, then there's 231 that's between 0 and 360. If I add another 360, there's the second solution that this point provides. So I had 4 solutions from 0 to 720 that satisfy this equation, and 2 of them are right here. If we take the sine of 591.08, we're going to get this negative ratio. And again, it's rounding it to 2 decimals, but you can see that it is a solution. All right, so let's go to the next one. So again, we're expecting 4 solutions. We're expecting 4 solutions. I know that for cosine, I look to the x coordinate, and x is going to be positive in quadrant 1 and in quadrant 4. And when I use my calculator to find an inverse with cosine, it only uses the upper half of this unit circle. So it's going to return a value that's between 0 degrees and 180 degrees. So if I go inverse cosine of 0.893, that's one of my solutions, one of my 4 solutions. And it's coming from this point. So if I add 2 pi, that'll be the second solution. Because see, this point is providing infinitely many solutions to this equation, but of those infinitely many solutions, we're just looking for the ones that are bigger than 0, bigger than or equal to 0, and less than or equal to 720. So here's 2 of those 4 solutions I'm expecting. Now, let's come back and use this angle as a reference angle, and let's jump to this point. Let's jump over here. Well, these are both the reference angles associated with these 2 points. So if I take 360 minus that, if I take 360 minus whatever this reference angle was, I didn't write it down. So there's the first of the 2 solutions that this point is providing. Take the cosine of this angle, and you're going to get 0.893 or something approximate to it. Add 360 to this, and the same thing. If you take the cosine of this, you're going to get something approximately equal to 0.893. All right. Let's move on to the next one. We're still. Oh, wait a minute. I have more than. I still have my old directions here. So I think the new directions have changed for these two problems. Let's double check that. No, I still have that open. I do. This is that answer key that should be on headline. So the directions changed for 22, but for 21 I'm still doing 0 to 720. So for 20, so this direction is here, and this direction is for this one. So let's not confuse me. I'll take this and put it on its own page. Two directions. So here, the directions are still we're still in degrees. We're at these infinitely many solutions that satisfy this equation. We're only looking for ones that are between 0 and 720 on that first two revolutions around the unit circle. Let's see this in. Let's go back and get just a blank circle to use as reference. Alright. Tangent is positive in quadrants 1 and 3. So there's a point that has coordinates x, y that has a ratio of y divided by x that's equal to 0.6. Alright. And these are y and x are both positive. Down here, these same 2 points, x and y, are both negative, and that ratio is the same. So when I go to the calculator, however, the calculator treats this inverse as a function, not as a relation, and it returns a single value that's between negative 90 if you're in degrees and positive 90. So it's going to return this value. Alright, so let's pull up the calculator. Let's double check. I'm in degrees. I'm only rounding to 2 decimals. That's fine. So the inverse tangent of 0.6, 30.96 degrees. Okay. The nice thing about the tangent with having a period of pi, that if we add pi, we get another solution. So of the 4 solutions on 0 to 720, here's one of them, and I just have to add 180 to get the next one, and then add 180 again. And here's 3 of the 4 solutions. Add 180 again, and I have my 4th solution. I'm done. So there, and see, that 570 is less than 720. If I add another 180, I'm going to be too big. I'm above the 720, so I found the 4 solutions that we were looking for. All right, now here we can write the general solution. So let's grab this to use just as a reference. The inverse cosine. Remember, cosine is associated with the x-coordinate. If cosine is positive, then I know that that's occurring here in quadrants 1 and 4. So the calculator is going to return a value that's between, I'm going to go back to radians, it's between 0 and pi radians. And since I'm in radians, I'm going to extend this out to more decimals. Alright, so the inverse cosine 2/3. Remember now there's infinitely many solutions to this. And this point is providing infinitely many, which is 0.8411 plus any coterminal angle to it, where n is any integer, and the integers are 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. When you're in quadrant 1, it's its own reference angle, so I can take 2 pi minus this, minus this reference angle. And this 5.4421 that's in reference to this point, this angle measure is right here around, and any angle that's coterminal to that plus 2 pi n. So there's all the possible values. There's all of the solutions that this describes, the infinitely many solutions there are to this equation. All right, so let's steal our the inverse sine is going to return values using the right half of the unit circle. Sine, I associate it with the y-coordinate. This is positive. This point and say another point over here in quadrant 2 both have a height above that x-axis, both a y-coordinate that's 0.344. And I know that exists because that's in the domain between -1 and +1. So when I take the inverse sine of 0.344, it's giving me this angle. And any angle that's coterminal to that is also a solution. Now, that's also its own reference angle. So if I take pi minus this reference angle, then I'll have this angle that's over here in quadrant 2. It's the radian measure of that, and then any angle that's coterminal to that point is also a solution. So the solutions to this equation come from these 2 points, and all of for those points being the terminal side of an angle, and any angle that's coterminal to those 2 angles. All right. Let me pause this for just a second, get a drink of water. All right, I'm back, and somehow I noticed that I'm getting the wrong. The 24, is that the direction? Somehow I pasted the wrong directions. The 24, all possible values. So it's not this 720 there. It's this guy, which I believe was the solutions here. All right. Let's steal our unit circle. All right, now, like I say, we're trying to find a ratio for tangent of point y divided by x with this negative 1.855. Negative ratios for tangent are going to occur in quadrants 2 and 4. When we go to the calculator and we ask it to return a value, it's going to return values that are between negative pi over 2 and positive pi over 2. And for this one, it's going to return this angle. So if I go inverse tangent of negative 1.855, it comes back with this negative value. Now this time, it's not saying that it wants all possible values. It's not saying I have to be bigger than 0. So I can just use this. And then from here, I can describe all the solutions by just adding pi to get to the next point, and then add pi to it to get back to that point. So here's all of the solutions with the period for inverse tangent, for the period for tangent and cotangent being just pi. All I need is one equation to bounce back and forth between these 2 points, because They're separated by pi, not by 2 pi. 2 pi gets me back. I would skip over that point, and I need both of those points in my equation there. So there's my answer for 24. Inverse. Now this time I'll give the all possible solutions, and then we'll just replace n with -2, -1, 0, 1, and 2. So let's paste our circle. Sine agrees with the y coordinate. Sine is going to be negative. There's going to be a point here in quadrant 3 and a point here in quadrant 4 that has a y coordinate that's -6/11. But when we go to the calculator, it's only going to look, it's going to treat this inverse sine like a function, but it's only going to look for values that are between negative pi over 2 and positive pi over 2. So when I have inverse sine of -6 divided by 11. So it's negative. Now, it does depend where I define 0 to be at. Remember that I'm just going to use this as 0. Now, I'm not sure if that agrees with the answer key or not, but if you show your work, you can argue that, hey, you're calling this 0, and then you're finding your coterminal angles by using that point. Now, if I jump over and write the equation for this point, then let's use this as a reference angle, and if I find that reference angle in quadrant 1, okay, so that's this angle. So if I add pi to this, then I'm all the way around here, and I'm to that point that I want to be, 3.7185 plus 2 pi n. So 3, 4, 5. They want 5 solutions from this equation, 5 solutions from this equation, I believe. So, but like I say, this one will depend on, are you calling the negative n equals 0, or are you adding 2 pi to that? And then for what my n equals 1 might be some people's n equals 0. So it might be just a shift, but I would count it correct. I mean, it's the idea here is what they want. So if we go second inverse sine of -5.769, there's my n equals 0 one. Now, why did I take it? I want to take it as this -6/11. Sorry about that. Ignore that. I have to take the inverse sine of a ratio, not an angle measure. That wouldn't make sense to do that. All right, so when n is 0, I have this -0.5769. If I add 2 pi, then 5.7063. If n is 2, if I go back to my 0, if I let this be -1, so if I subtract 2 pi, subtract another 2 pi. Like I say, if your table will have these same entries, but we might have a shift of where we called n equals 0 at, right? Of this infinitely long list, it's a little bit arbitrary how we assign n equals 0. I assigned it just on the first value that the calculator gave me. So we do the same idea over here. I don't know if I'll do them all here for you, but you get the idea. Inverse sine of the 6 divided by 11 gave me my reference angle, plus pi got me to my n equals 0. So then if I want 1 and 2, I'm just going to add 2 pi for n equals 1. For n equals 2, add another 2 pi, because I'm 4 pi away from what I called 0. If I go back to 0, to n equals 0 here, and if I subtract 2 pi, there's a solution, and if I subtract another 2 pi, there's the solution. Okay, so let's do the same thing here. If we go inverse cosine of 0.762, it's going to return an angle that's, let's go get my, up in between 0 and pi. So here in quadrant 1, it's going to look for an x-coordinate, and it's going to find it here in quadrant 1, and it's going to return this angle. And we'll call that n equals 0, and then you'll just add complete revolutions. So you'll let n equals 0, let n equals 1, n equals 2, negative 2, negative 1 into this equation to find the solutions associated with this point. There's another point on the unit circle down here that has that same x-coordinate, and we want to start with this angle. So we're going to take 2 pi and treat this as a reference angle and say minus that reference angle, and that's going to provide us with a starting point for another family of coterminal angles. And again, all you have to do is replace n with these and do that arithmetic. Alright, so let's move on. Same idea here, but that the arc cosine is just a different notation for inverse cosine, right? It's the same idea. So let's get our unit circle. It's going to, when we go to the calculator, you know what? This was a relation. This had infinitely many points. This guy, being an arc cosine, is only going to have one. It's not going to have all of these solutions for this. It's just going to be what the calculator gives us. At least that's what the notation is indicating, that it only wants exactly one solution. So in a way, this problem isn't associated with this type of directions normally, because it's determine all possible values. Well, here, there's only one possible value. Over here, there's infinitely many. And of those infinitely many, we just described a few of them using these different values of n. You know, I may have that wrong on the answer key, but I'll have to check. The inverse cosine of negative 0.9. And so I claim that there's only one answer to this. It's the angle 2.6906 radians, and that's this this angle right here, and that's it. That should be the only solution. Alright, so let's take a look at these word problems and then we'll be done. We did these in class, but I can do them again. We've got a gold mine is located so many miles east of Eureka City. So here's Eureka City. If I go to the east, let's call this direction east. If we go 61.8 miles, and then we go south, let's call down south 47.1, and these each have units of miles. We'll be here at our gold mine. Yukon Cornelius. Wasn't that one of those Christmas special cartoons that his name was Yukon Cornelius? I don't remember if Eureka City was in the cartoon. I guess not cartoon, it was like the claymation. So here let's find this angle theta, and then we'll superimpose that angle theta onto our compass. So here, and with these type of problems, we'll set our calculator to degrees. So we'll take the inverse tangent of the opposite leg over the adjacent leg, 47.1, 61.8, they have the same units. So I'm going to round it to a couple decimals now. So let's go round it to 2 decimals, say, and let's put this in degrees. Alright. So if we take the inverse tangent of this 47.1 divided by 61.8, we're getting a theta, an angle measure of 37.31. But let's look at our compass. We're calling 0 degrees due east, the positive x-axis. This compass is calling 0 degrees due north. So we're going to have to add 90 degrees if we want this to be our 0. If we want to start on this positive y-axis at that 0, we want to describe this angle, so we just want to add 90 to that. So if we add 90 on our compass heading, 127.31 degrees, at least to 2 decimals. Alright, so let's take a look at this next one. It's the same idea. On a map, a water source is west 2. So let's call west to the left. Then north, let's call north up. And these are both in units of inches. So we want to find this angle theta, which is the inverse sine of 1.4, the opposite over, now that I almost said that the hypotenuse here, I'm getting sloppy on my picture, that 2.1 inches is associated with this leg. See the arrow? And this is the heading that I want. So I made a mistake by saying sine because I didn't make my drawing clear enough. It's the inverse tangent. Sorry about that. So if you're sloppy in your drawing and misread your drawing, you're gonna make a silly mistake. You might make a silly mistake like I almost did there. Alright, so let's take this inverse tangent of this 1.4, and both of these were in inches. Alright, so I claim that this theta is 33.56 degrees, but let's superimpose that on our compass, because our compass has 0 degrees being here. So we want to wrap all the way around to here, right? So we want to take 270 plus this. So we need this plus 270. So this 303.56, because from here to the start of this angle right there is 270, and then we found this extra part right there is the 33.56. Alright, so I think there's one more. Now this one isn't used in a compass, it's redefining its own 0 degrees to be in standard position like we do. 0 degrees is on the positive x-axis, so that's what we're normally used to. So we have a coordinate grid, so we just have a Cartesian coordinate system. The x and y are both negative, so we're in quadrant 3. So if I draw my x-axis and y-axis, if I call this 0, this point is here. So the angle that I want, yes, I thought I changed colors, is this angle. But I'm going to use this reference triangle to first find this angle, and then I'll add 180 to it. So if I take the inverse tangent of the y coordinate divided by the x coordinate, the negative signs are going to cancel, so I'm not even going to bother keying them in. 46.29 degrees, but I need to add 180 to that for this problem. So I want to tell our robot that this angle, theta, if I want to call it, or whatever we want to call it. Sometimes you'll see, let's call it beta, just to be different. 226.29 degrees. Alright, so hey, I hope that helps, and I'll talk to you later.